Okay, it's the top of the hour, and I want to welcome everybody to this month's installation of From Research to Implementation webinar series that we have here at NCAT. It's a pleasure to see you all here again today. We've got a little bit of a different format today, which I'm very excited about. We're actually going to have 4 different topics from different presenters here at NCAT. We're going to talk about the significant findings from the 2021 test track. And we also call that the 8th cycle. So if you hear those words together, you'll know that's the same thing. So what we're going to do today is we are going to talk about recycling agents with Dr. Nam Tran. We're going to talk about CCPR for low volume roads with Dr. Ben Bowers. We're going to talk about the balanced mix design life extension with Dr. Fan Yen. And Tom Harmon, my good friend, is going to talk to us about inner layers. Once we're done with all those presentations, we'll do questions from there. So please make sure you keep yourself muted during the webinar and type any questions that you have into the chat box, and we'll go from there. So given that, I want to turn the time over to Dr. Nam Tran.
Good morning, everyone, and thank you very much for quick introduction, Travis. So today I'm going to talk about the balanced mix design experiment that we have at the test track using recycling agents with the high wrap mixture. And first of all, before we delve into the technical details of this presentation, I would like to acknowledge the sponsorship from the Cargill Bioindustrial. And of course, as we cannot have this project done without the Cargill support and sponsorship. And they sponsor the test section entry at the test track. The objective of this study is to design, produce, and place the 2 different high wrap mixture on the test track. The first made with 30% wrap without rejuvenator, but it was produced with a compaction aid, and I'll talk a little bit about that later on. And the second make had a 45% wrap mixture with the bio-based recycling agents. And the 30% wrap mixture was one of the makes that had been approved for use in the state of Virginia at the time. Dr. Ben Bowers here was still one of the research engineer at the BTRC, and then he was assisting us in selecting this mesh design for the experiment with Cargill. And both of the mixture was designed with the balance to balance the rotting and cracking resistance on the test track. So if you are not familiar with the structure of the test track is an oval track that 1.7 miles long, and the Cargill test section is on the north side, on the north tangent of the test track. And the section N3 was subdivided into the 2 subsections, N3A and N3B, and the two sections was built on the same structure. The only difference between the 2 structures is the surface mixture. Section N3A was paid with 30% wrap and compaction aid, and using PZ64-22. Section N3B was paid with 45% wrap mixture with the same version binder, but in addition is the recycling agent. And the 2 mixture was designed to meet the Virginia BMD special provision at the time. And then the requirement is to have the maximum rod depth in the APA of 8 millimeter, and then the minimum CT index of 70, and then it also requires some maximum mass loss in the Cantabro test of 7.5%. So the first step that we did in this study is to look at just only the volumetric mix design. So we get the 30% wrap mix design from Virginia. We produce in the lab, and then we test it using the CT, the ideal CT test to determine the CT index, and then also the run the APA rotting test. And then as you can see here, both of them make with 30% wrap and 45% wrap was in the the corner that we call it brittle. What that mean is this mixture, both of the mixture pass the rutting but fail in terms of the cracking. And the next step, what we did is we tried to determine what would be the optimum doses of the rejuvenator that Cargill provided. And what we did in here is that we test 3 different doses. I believe that maybe around 1, 3, and maybe 4.5% rejuvenator at the time. And then what we found is that the medium doses of 3% rejuvenator worked the best. And then with 3% rejuvenator, we was able to increase the cracking resistance of the 45% wrap make to be similar to the cracking resistance of the 30% wrap make. But after this step, as you can see here, both of the make was not able to meet the minimum CT index requirement of 70 set by Virginia DOT at the time. And the next step that we did is we had to add a virgin asphalt binder to make both of them make pass the cracking requirement. So you can see here the 30% wrap make with volumetric only require 2.5% AC. And here, if in order for that make to meet the cracking requirement, it require 5.5% and then 45% wrap with 3% recycling agent. The volumetric make design require 5.2% AC, but in order to meet the balanced make design requirement, it need 5.8% AC in the mix. So here's the quick summary of the mix design that we have, and then I would like to point out a few things that you can see on this slide here. So first thing that if you look at the true mix design, 30% wrap make and 45% wrap make, you can see that total AC can be very different. For 30% wrap, 5.5%, and 45% wrap is 5.8%. But if you look in the details, the virgin binder content is really different. And then you can see here the 30% wrap make will have about 4.2% AC, and the other mix have only 3.6%. So still 0.5% AC different. And then 4.45% wrap has lower binder content. That would maybe offset some of the cost that you need to use to pay for the recycling agent if you need to. So after that, both of the mix was paved on the test track, and you can see here both mix was produced as the hot mix, but there's an incident at the test track that caused a delay for the section N3B. So that section N3B with 45% wrap make and with recycling agent was compacted at much lower temperature, similar to the maybe warm mix. But both of the sections meet very high density requirement. In this case, you can see that above 96% without any issue. And then you can see here that there are some concern about from some state when they try to use a balanced mix design, the QCF void is very low. So in this case, you can see that the QCF void for both the mix, especially for the make recycling agent, 45% wrap, only 1.5%. So there is concern at the time that some of this mix here may have the rutting issue on the test track, but Cargill decided that they would like to try that and then see if there's any issue with that on the test track. So fast forward 6 years after that first construction on the test track to the end of the research cycle back in April that we measured it, both sections still perform very well in terms of the smoothness. They are almost the same. One of the sections here, you can see that's N3A that look very rough at the beginning because we have some issue with transition area. After it fixes, it's smooth out, and then both sections perform the same. And then in terms of texture, they are the same. We changed the way that we measure the texture. That's the reason why you had the big jump here from mid texture depth to mid profile depth. or mean profile depth. That's the reason why that you can see a big jump there. And then in terms of rutting, you can see here that both sections still perform really well in terms of rutting, and then the rut depth is still below 7.5 millimeter for both sections after 20 million ISO. And then very minor cracking you can see in these two sections. And then here N3A have a little bit more crack than the section with the 45% reliable recycling agents. And here the crack you can see on the surface, the crack in section N3A is a little bit more severe compared with the crack on the section N3B. You can see here maybe the crack grinding on top surface, and then the file was maybe showing on the surface the crack on the left here. And then the crack on the section N3B, you had to look very close in order to see it. And then so the key finding is that both mixture can be designed with the BMD approach, and then it meets both the cracking and rutting requirements. And if you use a volumetric mix design, it's very hard to meet the BMD requirement at this moment. And for the balanced mix design mixture, you may not be able to meet all the volumetric requirements. So some of the state, when you require both the rutting, cracking, and then also volumetric, it'd be very hard for the contractor to design the mix. And then using the BMD mix, you can achieve the very high density, in this case about 96%. And then even with the low air voids, QC air void in the field, we don't see any rutting issue. And then both sections still show good performance. We know some very small rutting and then hairline crack after 20 million and 6 years on the dead track. So with that, thank you all very much for the time today.
All right. I think it is my turn. Can somebody confirm that you guys can see my screen?
Yeah, that looks good, and we hear you great, Ben.
Perfect. Thank you so much. Really excited to talk to you guys today about some of our findings, specifically with respect to cold central plant recycling, or CCPR, on low volume roads. Quick shout out to our sponsors that I'm going to be referencing sections for today. We have Soleil, we have Blackledge Emulsions, Pavement Restorations Inc., VDOT, and Ingevity as well. So before we dig into the low volume road side of this, I want to give a very brief history lesson. Our first dipping of the toe, if you will, into cold central plant recycling was back in 2012. So Virginia DOT had done their big project on Interstate 81, and they wanted to come down and investigate this material, cold central plant recycling, which, for those of you who are not familiar, it is 100% wrap as the aggregate. There's no additional aggregate. It's a cold process, and the material is stabilized with foamed asphalt at about, in this case, it was 2% foamed asphalt, so much less virgin binder going into this. That foam spot welds this material together, and so you have this really interesting matrix of material that can be used as a base layer. They also did have 1% cement in the mix to help distribute foam and get a little additional stiffness. So anyway, this was not something that they had done in a heavily trafficked area. And coincidentally, especially considering the title of this study, or this topic today, this was mostly only done on low volume roads, but they put it on the interstate, and they wanted to see what it would look like, and more importantly, how is this material going to fail, and how quickly is it going to fail when it reaches the end of its life. So they came down, they built 3 test sections. Each of them, you can see here, the first one in 3 had 6 inches of hot mix over top of 5 inches of cold central plant recycled material, over 6 inches of ag base on top of the subgrade. Section N4 was a little bit thinner. It was 4 inches of asphalt, so hot mix, over top of 5 inches of CCPR, over 6-inch aggregate base, so 2 inches thinner than section N3. And then section S12, which was the same as N4, so 4 inches of hot mix over 5 inches of CCPR, but they also had 8 inches of stabilized base. That was a cement stabilized base using the full depth reclamation process. So this was done, and those were the three sections. So you had a thinner section, kind of an intermediate middle section, and then a thicker section that had that stabilized base. So how did they do? You know, again, under this interstate level traffic, I think it's safe to say they did incredibly well. So we had that 6 inches of hot mix, over 5 inches of CCPR. After 20 million easels, it had 0 cracking, very, very little increase in rutting and IRI. Everything was very stable. At this point, VDOT said 20 million easels. We didn't even know that this would make it 10 million easels. Mind you, when we ran the AASHTO 93 guide on this material, I think it was supposed to fail by 2 million easels. Well, now we're at 20. We've well gone past the life expectancy that we thought we'd get. Decided to take it offline, but leave the thinner section in place as well as that thick section with the stabilized base in place. Now, that really thick section with stabilized base, ran it for 30 million easels. It had 0 cracking. It had very stable IRI and rutting, no changes. We deem this to be perpetual. This pavement, based on the strain levels it was experiencing, comparing it to other sections, full depth hot mix sections on the track, we believe that especially when you put that stabilized base in, you get perpetual performance out of it. VDOT actually implemented this cross section on the reconstruction of Interstate 64, which was done back in 2021 and 2022. So that has been implemented, which is great. We're not going to talk any more about that today, but I'd be happy to tell you more about it offline, so feel free to shoot me an email. And then the section, that thinnest section, that 4 inches of hot mix over top of 5 inches of CCPR over 6 inches of aggregate base, we saw the tiniest of cracks at 29.7 million easels. So VDOT said, all right, we're going to continue trafficking this. We're going to see if we can get it to 40. And it did last to 40 million easels, but we got to the point where some maintenance activities were going to have to be done. That section was actually taken out just a few weeks ago. So we're going to be reconstructing in that area. Now, what did this look like? We did the forensic analysis. We got to do the CSI thing. We cut it open. We trenched it. And what I want you to note here is that we're operating in the direction of traffic here. This is in the wheel path. And you see those yellow lines show up. These yellow lines, these are fatigue cracks coming from the bottom of the CCPR up into the hot mix. So point being, we wanted to know how this material would fail. We're getting a typical fatigue failure like we would in a hot mix asphalt. Now keep in mind, just to give you an idea, if you were to look at the air void content of this material, it's probably anywhere from 9 to 14%. That's typical for a cold central plant recycled mix. Again, it is done through a cold process. You just add some water, about half of your typical asphalt content through foam or emulsion, and then a little bit of cement. And this is what we got. So very interesting findings. We now know in a high traffic environment to US standards, this thing's going to perform. This is great news. And so this can be further implemented. But that's not what we're here to talk about today. What about these low volume roads? What can we be doing more with low volume roads? Because frankly, we have a whole lot more low volume roads around the country than we do these high traffic interstate roads that are the things that really get our big focus. So we put together what we refer to as the off-ramp study. The off-ramp study investigated typical foam or engineered emulsion CCPR with a thin overlay. We also wanted to answer the question of what happens if you add a rejuvenator. So CCPR does not use rejuvenating agents. We just use typical PG 6422 or whatever your typical binder grade is, foamed in the mix, or an emulsion that uses that same type of binder. But what happens if you use a rejuvenator? Because again, this is 100% wrap. Will it activate that binder? If it does, do we get some performance somewhere in between? And we had some very limited experience, something a contractor partner of ours did in their yard. They shipped us cores. I'll point that out to you real quick. So what you see here is this is typical hot mix. This third picture here, the one that's really faded, that is a foamed mix. It is 85% wrap. They did use 15% of a number 10, but you can see you got kind of like these blobs around. It looks pretty dry. And frankly, this pill would have flaked off in your hands. When we put it in that confined environment, though, it performs really well. This right here looks like an asphalt core. But actually 5 inches of this material is a rejuvenated CCPR. So it's 100% wrap with 1% foam. And of that 1%, 50% of that 1%, so 0.5% was a rejuvenating agent. The other 0.5% approximately was a PG6422. Point being, you can't tell the difference between it and the hot mix visually. And we saw when we ran some laboratory tests that we actually got modulus values somewhere between hot mix and cold recycled mix. So we were curious, what happens? Is this a good thing? Is this not? What can we do with it? So we built this off-ramp study. You see here the test track. The off-ramp, of course, is right here near where you come off to the main test track building. And we built 6 test sections. So one of the sections had 4 inches of hot mix, because again, we saw stiffness increase when we used rejuvenator. So we wanted to say, well, what if we just use hot mix? We also had 4 inches of foamed CCPR in a section, typical CCPR. We had 4 inches of engineered emulsion CCPR. This is a typical CCPR. And then we had 3 sections, each of which had a different type of rejuvenator. One was an emulsified rejuvenator. One was a straight rejuvenator. No emulsion was added, no binder. It was just a straight rejuvenator added to the wrap. And the last one was an anionic emulsion that had a bio-based rejuvenator added to it. All of these use the exact same wrap, with the exception of the 4 inches of hot mix, because we weren't making 100% hot mix or 100% wrap hot mix for this study. Now, at the end, all of these sections had what ended up being a 1-inch 475 thin lay. So very thin overlay. Again, looking more at like what might actually be done if we had to do a structural reconstruction on a low volume road. Well, what if we could go out and actually just recycle that material that is there already and put a thin lay on top? Now, I don't have time to hit all the interesting findings we have here. Of course, that's in our report. I'd be happy to schedule a meeting with you and tell you more about it myself. But one of the big things that we noticed is we did 3 of the designs here in-house. The other designs were done by the folks we were working with. One was the foamed asphalt. So this is a typical CCPR design. We also did the straight rejuvenator and the rejuvenator that had emulsion and rejuvenator in it. So these 3 designs, 2 were rejuvenated, 1 was foamed asphalt. And what we saw is the density actually increased when we added the rejuvenator. So you see our bulk dry density of our foamed mix was 126.6. It's much less than hot mix. Keep in mind, higher air void content. When we use straight rejuvenator, with the same exact wrap, we got 134.4 pounds per cubic foot. And then when the emulsion plus rejuvenator, we got 130.9. So wrap gradation's the same. What's the difference? We believe that we were activating some of that binder and allowing it to meld together, ultimately leading to lower air voids and a higher density. So activation of that binder, we do believe we're seeing that when we rejuvenate. Now, when we built these sections, we gave 2 different plant options. Again, thinking about low volume roads, what's nice is with CCPR, we can actually take the plant out to the field. You see a Vertgen KMA here. That was done for the foamed asphalt and the engineered emulsion. We also had Pug Mill Systems from Pavement Restorations Inc. come out. They brought their Pug Mill Systems portable pug mill, and all of the rejuvenated mixes were built using this plant. Here is a nice picture of everything except the hot mix, because I'm hoping all of you have seen hot mix paved at some point in your life. You see the foamed mix, the engineered emulsion, the emulsion plus R1, the straight rejuvenator, and the emulsion plus rejuvenator 3. All of those, of course, were one continuous pass of a 1-inch thin lay. When we look at cracking, we started to see cracking show up in the emulsion plus bio-based rejuvenator pretty early on, and I'll talk about why in just a second. We also saw a little bit of cracking show up in our cold recycled rejuvenator product. Now, when we look at roughness or IRI, we actually see that we go off the map pretty quickly with that anionic emulsion plus bio-based rejuvenator. Again, I'll talk to you about why that occurred here in just a second, but I want you to know, yes, like we saw horrible roughness here. I'll also note that our typical cold recycled mixes were pretty standard. So they stayed pretty flat. We did see a little bit increase with that straight rejuvenator, but it stabilized as well. And we saw the exact same trends with our rutting. Okay, so one went off the charts. Again, it was that bio-based rejuvenator in the anionic emulsion, and the straight rejuvenator had a little bit of an increase. But overall, our typical cold recycled products, as well as our emulsified rejuvenator, they stayed pretty consistent. Very little rutting, very consistent. So what happened with that one that went crazy? Well, we believe that based on our experience during construction, we had an emulsion type that was not appropriate in this specific case. So that anionic emulsion had a lot of water in it. We also activated binder, and we had a lot of hygroscopic moisture in the mix already. So that could have led to an issue of needing longer to cure. This material did sit over the weekend before it was placed. We also, when we were rolling it, had moisture and emulsion pressing up from the surface. That is problematic. We got off the mat and waited and then got back on it. But ultimately, we think it needed even longer to cure. So again, that we have placed these mixes, not the rejuvenator, but a foam mix, for instance, we placed it and overlaid it 12 hours later. So there was something going on here. We do think we have corrected it, and we plan to repave it this summer, and we'll be happy to report back on what happens then. We're going to make some changes in the emulsion we use, as well as some of the other things that we're doing for that section. But overall, most of the sections look great after 180,000 easels. So we get about 1% of the total traffic on the off-ramp because it's really only used when they're pulling off. And so it is more of a low volume type road. Now, in conclusion, CCPR can be used both in low and high volume routes. So I want to emphasize, we've talked a lot, and if you come to NCAT test track conferences, we're talking a ton about high volume routes, but we should also be looking at this in our low volume roads. We can also use a thin overlay for this material. It is protected, and that's what matters. We have seen cases, not specifically here, where they've used a triple chip seal. So there are different options that we can use to actually bring up the standards on our low volume roads and actually correct problems. We're not just going to Band-Aid, we're actually going to remove cracks and recycle that material in place. Now, some, but not all of the rejuvenated CCPR mixes performed at least equivalent to the CCPR and dense graded mixtures with a thin overlay. And then the question I want to leave you with, and something we're exploring here now, is what if we had not put an overlay on it with the rejuvenated mixes? Now, we wouldn't do that with a typical CCPR due to potential raveling, but if we're actually activating binder, what if you could go out and you could place a CCPR mixture on a low volume road and get more structure, but also not have to place that overlay on top or do any kind of treatment on top? That would be a big win potentially for our local highway agencies and folks who are managing these low volume roads. So with that said, if we have time at the end, I'll answer some questions, but you can contact me at bfbowers@auburn.edu. I'm super searchable. But I'm now turned it over to Fan Yen.
All right, it sounds good. Thanks, Ben. Let me share my screen. All right, can someone give me an indication that you can see my screen okay?
That looks great, Fan.
Okay, all right, sounds good. Thanks, Travis. Well, good morning, everyone. We're very glad to have you here today with our webinar. We're gonna, for my presentation, I'm gonna kind of like switch gear a little bit from the CCPR, the great discussion that Ben had. We kind of like change back to balanced mix design. For the topic that I talked today, I mean, it's a specific section sponsored by Texas DOT, so I do want to give a shout out to them for sponsoring the sections or the experiment on the track about this experiment. So I'm sure like many of you on the call today have done quite a bit of work with balanced mix design. If you look at where we are, there's a significant amount of work being done to look into like, we got a volumetric mix design. And when we run the performance test, we realize some of the mix designs may not have balanced performance, right? And therefore they need to do some like a design modification to improve the performance. Either you use a high temperature IDT for rutting evaluation, ideal CT for cracking, or any other combination. So there's lots of effort out there to say like how we can modify the mix design to give us a better, test results, right? And then I'm sure like many of you, like including myself, have been asking, well, what happens, if we do the design modification, we got a better index test result. How does that affect the payment performance, right? I'm sure like many of you have heard, we have been saying that one of the benefits about the balanced mix design is to improve mixture quality and eventually improve the payment performance. So do we have information to justify that life extension benefit associated with balanced mix design? And that is exactly the ultimate objective of the section that I'm going to talk to you today. So with that being said, TxDOT, back in 2018, TxDOT and NCAT, we got together, we talked about the experiment, try to explore that question that I just mentioned. So the objective we did on the test track was to look into the performance comparison of surface asphalt mixes designed with the volumetric approach versus balanced mix design approach. So with that being said, you can just think about like we put sections next to each other on the test track. One is volumetric approach, the other is BMD, and then we'll let them, compare to each other to see how they perform, on the track. Back in 2018, we started two sections, S10 and S11. S11 is our volumetric control, and S10 is our experimental section with balanced mix design. 3 years later, in 2021, TxDOT added another section using the same materials, and but with a little bit different, performance criteria as what we did in 2018 to add to the experiment to see how they compare with the two sections we had in 2018. One interesting perspective about the experiment we have here on this experiment is that all these three sections have fairly challenging underlying condition. This is kind of like a more to simulate what we have in real life, right? If you have kind of like a challenging underlying condition, you just do overlay on top of it. Can balanced mix design still provide that performance enhancement as compared to the volumetric mix designs? So that's kind of like the final objective of the experiment. Just a little bit of information about the mix design. It is a TxDOT 12.5 SPC surface mix. On the gradation side, this is course graded. This is an important piece of information because I'm gonna, give you a little bit more information on that perspective on the next slide. All three mixes use the same SBS modified binder. The same cold fit percentages and fractionated wrap. And we try to keep the wrap binder replacement ratio the same at 20%, which is very typical in Texas and also very typical in this part of the country. I'm sure like many, for those of you who have done balanced mix design before, like there's different options on the BMD toolbox that we can use to improve performance, right? But the specific approach we used in this experiment is to look into the gradation change. I mentioned earlier that, the mix design that we use in this experiment is course graded. So in order to improve the cracking test result, what we did on the design modification was even make it coarser, okay? So we kind of like push the gradation, away from the maximum density line so that we can create more void structure within the mix. And that will allow us to put more asphalt binder, but still maintain that 4% air void and the volumetric requirement that TxDOT has for their BMD specification. Because of that change in gradation and more asphalt binder added into the mix, that gave us higher VMA, but more importantly, higher VBE. And that is kind of like how we're hoping that the higher VBE is going to give us better cracking resistance. But once again, like, balanced mix design is not just about adding asphalt binder. There's different options that there can be used. But for this experiment, this is the specific approach we did. This is a kind of like a quick summary of the volumetric information about the three mixes. I highlight the binder content information here. Just want to show like how different they are. The S11, the volumetric control section, have 4.7% asphalt binder content. This is kind of like the borderline mix, but it does meet TxDOT volumetric requirements. And then when we did the BMD modification, because kind of like what I explained earlier, we need to put more asphalt binder to improve the cracking resistance. And that's why you see like a significant higher binder content when we look at, S10 BMD from 2018 and also like N6 BMD section from 2021. So if you look at the difference, we're talking about like 8/10 and 6/10 more asphalt binder, which I know is a lot, but if we can make the payment last longer, the life extension benefits should be able to justify the initial cost because of the more asphalt binder. And that's kind of like the comparison that we have in this experiment. So this is a performance diagram very similar to what Nam showed earlier for the rejuvenator section. Pretty much like we put the cracking test result on the y-axis and the rutting test result on the horizontal axis. And the two dashed lines represent textiles BMD criteria for the surface mixes. And then with that criteria, we kind of like divide the performance diagram into 4 zones. With the one highlighted in light green color here is what we call like the sweet spot. This is where like, the mix, according to those BMD test results, should have like a balanced rutting resistance and cracking resistance. If we look at the test result, start off with S11 volumetric, have very good rutting resistance. That's what we saw on the Hamburg with the Hamburg testing, but it did not perform quite well in the overlay test. Which is not surprising because like just looking at the mix design with the 4.7% asphalt content, we know the mix is definitely on the dry side. And with the dry mix, that's what we have, right? Very good rutting resistance, not so much on cracking. After we did the BND modification, adding like, with the gradation change with more asphalt binder added, we were able to move that data point into the sweet spot. Okay, as you can see here, S10 was within the sweet spot, and N6 was kind of like right at the borderline, and that's exactly what TxDOT want us to do. So design a mix. So with the cracking performance that is right at the border of the overlay criteria, and see how that section perform. So this is kind of like, just to prove like the design modification we did works really well. Not only we were able to improve the cracking resistance, but also we were able to maintain the rutting resistance so that the BMD mixes will have balanced rutting and cracking. And that's what we saw with the Hamburg and overlay test. If we look at the rutting performance on the sections, the 2 sections from 2018, they have been in place for like a 20-minute ESOL. That's why like they go all the way to the right side of the chart. But the other section, because it was placed 3 years later, so it was only like has gone through like 10-minute ESOLs. But overall, like we did see some rutting in those sections, but if you look at those numbers, they're somewhere between 0.2 to 0.3 inches. Which is still far from the 0.5-inch rutting criteria that we use in the field. So rutting is not a concern, and that's something like confirm what we saw in with the Hamburg testing in the lab. The interesting part is about the cracking performance. The N6 section that was placed in 2021, we haven't seen any cracking up to 10-minute ESOL, so there's no data point here on the cracking side. But if we look at the 2 sections from 2018, the blue curve is the volumetric control section. It started showing cracking about like a 5 to 5.5 minute ESOLs, and then like it really took off in terms of crack propagation. And then, but if we look at S10 BMD, first of all, it didn't have any cracking until like a 9-minute ESOLs. But even if it started showing cracking at that point, the crack propagation was so much slower as compared to the volumetric section. Just want to give you a picture of the cracking we saw on S11. At that point, the section exceeded the 20% cracking criteria, and also roughness was through the chart. And that's where we decided to mill off the section and call like end of life for that section. But if we look at the cracking data for S11 and S10 and using the 20% criteria that we use on the test track as kind of like the end of life criteria, and you compare the blue curve versus the orange curve, and this is where we say like with balanced mix design, it provides like over 5.5 minute ESOLs life extension on the overlay life, okay? And if you compare that against, what we see on the S11, that's almost like more than 30% increase in overlay life from balanced mix design on the surface mix. So with that being said, this is definitely a field section that, improved pavement performance by balanced mix design. And with life extension that we can get from balanced mix design, it definitely has a great potential to provide, significant economic and environmental benefits, from the life cycle cost or, life cycle assessment perspective. So with that being said, balanced mix design does provide a pavement life extension benefit, and that's what we saw from this experiment. So with that, I will hand it over to Tom for him to talk about the interlayer study.
Thanks, Ben. I pushed too soon, so it yelled at me. Give me 1 second. All right, so I get to kind of wrap up today's discussion. I feel like I'm at a mini track conference workshop, which is pretty fantastic. When we typically do this, it takes several days and a lot of information is processed quickly. So I'll be talking about how do we prevent reflective cracks. So Georgia DOT has sponsored over several cycles test sections out at the track looking at different interlayer approaches. Back in cycle 5 of the track, which started in 2012, we milled down a perpetual pavement and then created a cracking pattern, sawing full depth through the asphalt, which basically influenced about a third of the sections for reflective cracks. So if you can imagine, every 3 feet longitudinally and every 15 feet transversely, we sawed down 1/8 inch wide and then filled those back with sand so that we felt that the cracks were actually working. In the original study, we looked at 2 different interlayers. One was a 0.7 inch double sand seal coat, and the other one was a little over 1 inch open graded interlayer, or OGI. With both of these, they did exhibit some cracking at the end of 2 cycles of traffic, so 20 million easels, but those cracks were very tight, so less than 1/4 inch, so low severity. The 0.7 inch double sand and steel did exhibit rutting. That was over 1/2 inch, it was 0.8 inches, where the OGI only had about 1/4 inch of rutting after 20 million easels. So at the end of these 2 cycles, those 2 test sections were milled back and then cleaned and resanded. So this is a picture of the milled back section. And then 6 different treatments were tried in this area. First 2 were geosynthetics, and Georgia allowed the Geosynthetic Materials Association to pick what products would be looked at. And it is my understanding they literally put the names of their members in a hat and drew out 2. So Asford Saint-Gobain's glass grid was selected along with Petromat. So these were the first 2 cells within the section, which is pictured here during construction. So in the background, you see the glass grid. It's a CG100 product being placed on a 6422 tack coat, and then the Petromat is following after that. Now, I have a note in here that the Petromat, when specified, they like to have a tack coat that's a PG70. And on this particular application, just for uniformity, we used the 6422 on both sections. But you'll see in a minute, it did not appear to impact the performance. Heading down the sections, the next one was a virgin chip seal, which is the lighter so. And in the background, you see a wrap chip seal that was placed. Both of these use the same tack rate, and that becomes significant with regard to rutting. We actually think we should have dialed back the tack coat for the wrap chip seal because the wrap is already coated, and that we did see a little bit more rutting in the wrap section than other sections. The remaining 2 sections used a Blackledge Ultrafuse trackless tack at a dose rate of 0.25 gallons per square yard. We can see here the asphalt rubber gap graded, which is sort of like an Arizona product, but slightly leaner. And the very last one down there is going to be an open graded interlayer, another OGI that went down with the Ultrafuse underneath it. So for the findings, after 2 cycles, 20 million easels, we see very good performance in most of the sections where the rutting is around 1/4 of an inch. I already mentioned that the wrap chip seal, we think we gave it a little too much tack coat, and that was slightly higher, around 0.4. And then the asphalt rubber gap rated was somewhere in between. On the cracking side of the house, first cycle, no cracking at all. And it took a cycle and a half worth of tracking before we actually saw our first crack appear. And we used the Buzz-O-Matic 2000 to find that crack. If you don't know that joke, Buzz used to go crawl around on the actual surface and be able to find cracks that no one else could find. So right around 15 million easels, we saw our first crack, and that appeared in the asphalt rubber gap graded. And then much later on, almost towards the end of the second cycle, we saw a little cracking form in the wrap and also in the OGI section. So to kind of summarize these out, glass grid, Petromat are 2 geosynthetics, no cracking at all. The virgin chip seal after 20 million easels, no cracking at all. The virgin chip seal, the wrap chip seal, 0.8%, low severity cracking. Asphalt rubber gap graded was the highest with 3%, but also low severity cracking. The next slide is going to be Ben Bauer's favorite game to play with his students, which is find the crack. So here you can see the asphalt rubber gap graded inner layer, and there is a crack there. It's kind of hard to find. This is my best attempt at kind of mapping out where that crack is. But again, less than 5% cracking total. So to show what this looks like from a balanced approach, because we love to do things from a balanced mixed design approach, we take field performance and we compare rutting to cracking, and you'll get this plot here. So over on this side is rutting, cracking. The thresholds are not Georgia's. These are just general thresholds where, you know, the perfect sweet zone or sweet spot would be that lower green box. Still good performing in the yellow box. And then kind of the no zone where it's both cracking and rutting would be the upper right. The 2 purple boxes show us our original study where we had one that didn't crack but did rut. And then the other one which did show cracking, but didn't have any rut or very low rutting. But again, low severity cracking on this as well. If I take it, I zoom in on just this last go rounds worth of sections, you can see here extremely good performance with regard to crack resistance, and that was the goal here. But 2 of the sections did exhibit a little bit more on the rutting that we would like to see actually out in an open roadway. To kind of summarize this, and maybe I'm showing my age, I'm going to show you my version of Yelp. So I came up with my own Yelp rating system. And here we have 5 stars is the most wonderful rutting resistance you've ever had, 5 stars for cracking as well. You can see here in the top, all of them get 5 stars for cracking resistance, and they all get 4 stars because we got around that 1/4 inch of rutting after 20 million easels for the glass grid, the Petromat, and the virgin chip. On the wrap side of the house, it's getting the lowest number of stars with regard to its rutting resistance, and then the asphalt rubber gap graded and the OGI are both only getting 4. Or I think I give them 4.5. With regard to the cost data, and you can look at those bars, we did do an economic analysis and provided it to GDOT based on their numbers. That data is not going to be published, but this gives you a regular feel, a relative feel for the cost differentials with regard to the products. And to finish out my talk, let's take a quick walk down the test track, which you can't do this anymore because Nathan is already working on building the next sections out. So these sections have been milled out. Here's the glass grid. We have no cracking, around 1/4 of an inch of rutting. Heading down the track a little bit further, here's the Petromat. Very, very similar results. And then very, very similar results with the virgin chip seal. Slightly less rutting, but still right around 1/4. Heading out a little farther, here's where we see 0.8% cracking, and this is a darn good looking roadway. You see very tight cracks when you can get down there and actually see them. A little bit more rutting than we would like to see, but again, with that wrap, we think it was a tack coat issue. Heading down to the asphalt rubber gap graded, 3% cracking in there. And then lastly, going to the OGI with 0.8% cracking and about 0.2 rutting. So here's the takeaways from this. If you haven't looked at interlays, you should look at interlays. Matter of fact, as I was listening to Ben talk today, wouldn't it be neat to take a CCPR and put an interlay over top of it and then top it off? Because we are getting classical bottom-up cracking. It'd be nice to put one of these in. So the finding here is there's a range of approaches that are out there. Matter of fact, I was on LinkedIn today and I saw yet another approach using fibers that's being placed up in Canada, trying to look at mitigating crack relief. We did have slightly higher rutting, but hopefully I've said this now 3 times. We think that the wrap chip seal is probably a really good approach, but we were a little high on our tack. And then the asphalt rubber gap graded. The belief here with regard to the reflective cracking, we're seeing this is that was this material that had the most flexibility to it. And we thought that maybe that's what's causing the slightly higher cracking within that. So hoping to keep on time and give us 5 minutes for Q&A, I will bring this to a close and hand it back to the amazing Travis.
I don't know about amazing, but Tom, did I see, was that an eagle I saw in your photograph there?
Did you see what in my photograph?
And there was an eagle in one of those photographs of the road.
You know, I didn't do the War Eagle thing here. So for those who know, I'm very bad at the War Eagle chart chant because I messed it up at our track conference. But there were actually 4 War Eagles hidden in my slides. You have to go back and watch the recording to see them all.
There you go. Well, I'm not getting the green box. Are you guys seeing my screen okay?
I'm seeing your
Yes.
screen.
Okay, sounds good. I wanted to let everybody know that's on the call here that the findings from this cycle have been published and you can get them on our website. There's also a couple other documents on there that I think are very notable, and those are let me get the laser pointer here. There's key track findings that really cover everything that has happened on the track. There's some real key findings in there. That's a nice little document that's easy to read. And there's also a synopsis of this last cycle, which gives you a Reader's Digest version of the full test track report. So given that, here's the emails for everybody that we've had on today. Screenshot that or take a photograph of that if you need to, but you can always go to our website and look up any of the folks that work for us here. You can look up their contact information and reach out to them there. So we have had a couple questions come in. I want to make sure that we get those addressed. Nam had some questions come in that he answered. And so I want to kind of reiterate those real quick. The one question is that with the recycling agents, was the wrap fractionated for the 30 and the 45%? And Nam answered that yes, it was fractionated based on the number 4 sieve. And that work was done there. And another question was the virgin binder on the 45% and the 30% wrap mixtures calculated using an effective binder content, or was it 100% from the wrap? And it was 100%. So we didn't use any of those reductions there. Nam, do you have anything further you want to say about those?
No, I think that's good, Travis.
Okay, that sounds good. That sounds good. And then Tom, you got some questions that came in for yours as well.
Yep, I got them up on the screen. It is my understanding that a tack coat was applied, and it was emulsified tack coat across all of them before the overlay was put on it. A 9.5 millimeter super paved mix capped off all of these materials, so it was the same material going down. And then with regard to the panel movement, in a perfect world, we would have went back and actually put some strain sensors to see how much those cracks were moving. That was not done. And there is a slight concern that when the tack coat was placed, as you saw, we put a pretty good tack coat down, that some of that sand that was in the joints may have formed a mastic. And actually, we didn't get as much movement in the cracks as we thought. But we are going to be doing a similar study like this with Oklahoma DOT in the next track cycle. And we have talked about putting some kind of measurement devices in there just to see how much those cracks are opening and closing on it.
Okay, that sounds good. That sounds good. Just had another one pop in here real quick that said that we often see a lack of bond at the dry interface that leads to top-down cracking with an overlay of with fabrics. And so I don't think there were any. Were there any? Oh, I guess it was the Petromat, right? It was a fabric that you guys used. So,
Yeah, we didn't see that on this one at all. And having just milled up the Petromat, you can see that it was very much part of the pavement structure itself.
Okay.
So that just was not exhibited on this.
Okay, that sounds good. That sounds good. All right. Always kind of want to plug a few of the things that we have out there. Training in Your Pocket is something that we're excited about. We've got a couple of new ones of those that we've got filmed that are about to come out. So please watch for those. Pass those along. Subscribe if you will. Even watch. There's some shorts have been coming out. Some little shorts that kind of that pull people to look at those. So give that a look if you get a chance. Also want to talk about our training courses that we have. We have all sorts of training that we do here for DOTs. We do them for the industry. We do custom stuff. We have some great opportunities. This photograph here happens to be from, we were teaching for an LTAP on that day. And then I also want to push out real quick to everybody that's here that our professor training course is going to be coming up the summer of this summer actually of 2024. And so, I'm sorry, let me push that, of 2025, summer of 2025, we'll be doing our professor training course. So if you know professors that need that education information and that content to teach asphalt at their universities, we would love to hear from you or love to hear from them so that we can make sure fill that course and make sure that we're putting the right information out there for young engineers who are coming through school. So given that, I do want to, first off, really thank all of our presenters today. I appreciate all of you taking the time to kind of boil down what you did during the conference, boil down that information into a short, digestible little chunk that we could push out today. I think this was really fun. I liked Tom's comment about feeling like a mini test track conference because it did feel that way. And then I want to invite you next month. We're going to continue our series. July 18th is our next version. That QR code, anytime you find that is for the next one. We've got a couple topics. I need to get a speaker confirmed. Once I have a speaker confirmed, I'm going to be able to release that topic, and that probably should come out maybe the first of the month when I get that topic that we can push out there, and we'll go from there. So given that, I want to thank everybody for joining us. And we'll see you next time.